Okay, so in this session we start the topic of learning. So, uh, we know that learning is a very important concept in uh, in AI. So, we will talk about learning over here. So, what is it that we have to learn in what the agent specifically? What is it the agent has to learn? So, first of all, it needs to be able to improve its performance on future tasks. About after seeing what is happening in the environment, etc., whatever performance the agent carries out at this point in time, is it possible to improve that in some way? Another thing is learning from examples. So, if you have a collection of input output pairs, then if you get a new input, then what would be the output for that? Or in other words, classification task. Um, and what we are going to do is we are going to look at a number of different classifiers which are used in practice: linear models, nonlinear models, um, non-parametric models like nearest neighbor, etc., support vector machines, etc. So, we will see a number of learning algorithms, and we will see how combining different classifiers or getting an ensemble of classifiers, how it can be used to give a better performance than using just one single classifier. So, what is the learning which has to be done in the agent? Um, you have to see which components have to be improved, what is the prior knowledge the agent has, what representation is used for the data, and what feedback is available to learn from. So, looking at all these things, you have to decide what is the learning algorithm you are going to use. So, because each classifier uses a separate type of representation, um, and according to the feedback, because in what way does the system have to learn. So, there are different types, like you may have feedback or you may not have feedback. If you have feedback also, how much feedback do you have? So, looking at all this, you can decide what is the classifier to be used. So, what are the components that need to be learned? A direct mapping from conditions to actions. So, if these are the conditions, what is the action to be taken? So, if you have a you may need to develop a sort of table lookup. Then inferring relevant properties of the world from the percept sequence. So, we saw right at the beginning how the agent behaves and about the percept sequence. So, looking at the percept sequence, the agent has to decide what action to take. So, how do you infer that? And then information on the way the world has evolved. So, obviously, the agent has an idea of what is happening in the world, because it is sensing what is happening in the world. So, looking at that, how the agent has to evolve in its knowledge and what action the agent needs to take. And then utility and action value information. So, in other words, um, how does it make a decision on what action to take. So, decision theory basically, which includes both probabilities as well as utility theory. Okay. So, depending on the information you have, what is the action that needs to be taken, and this action depends also on the utility or the preferences of the agent. And then the goals. So, this is the goal. So, if this is the goal, then what is the next step to be taken by the action, by the agent. So, these are the different things which need to be basically learnt. First of all, how is the representation of the knowledge? So, representation could be like proposition of first order logic. So, we saw when we did logic how knowledge can be represented in the form of first order logic or propositional logic, where you have facts and rules, right. So, the facts and the rules together make up the knowledge which is there in many systems. And then you may have a Bayesian network which includes the probabilities of the various components, and some type of a factored representation. So, or you can have input output pairs. So, how does this input output pairs actually work? You may have for example, so you may have features say f1, f2, f3, f4, and these features will have some values, and you will have an output which gives you the class label of that pattern. For example, if we take say digits 0 to 9, so the digit will be your input. So, the digit will be in the form of pixels. Okay. So, you have pixel information, and these pixel information can be all concatenated together to form your pattern, and then we have the class label. So, the class label is the output of this particular pattern. So, that is how we get this input output pairs. And deductive learning is from rules. So, we have rules, and how do you deduce a new rule from that? For example, all crows are black. So a particular crow 1 is a crow, and therefore, it is black. So, that is the deductive learning which we are basically talking about. And then learning according to the feedback that you are getting, right. So, the first one is unsupervised learning, where you have no explicit feedback, you are just given a set of patterns. So, what you can do basically is you can see what is the distribution of these various patterns, and you can see which pattern is similar to which pattern is dissimilar to which pattern, etc., and make use of that. So, that type of learning is called the clustering or the unsupervised learning. Next is the supervised learning. So, you are given some example input output pairs, and the agent will learn a mapping from the input to the output. So, when it learns a mapping from the input to the output, when you get a new pattern, it will take that input and find an output for it. And third one is reinforcement learning. So, in this case you have some feedback coming in, but not like the feedback you are getting in the case of supervised learning. You just have something like rewards or punishments. For example, when you win a chess game, when the agent wins a chess game, it knows that something was right. So, nothing needs to be done, but when there is a loss, it means something needs to be changed. So, what you do is the agent has to decide what is the thing that needs to be changed and change it. So, this type of learning is called reinforcement learning. And the fourth one is called the semi-supervised learning, where unlike in supervised learning, you just have a few labeled examples, not a lot of them, and most of the examples are unlabeled. Okay, so, the number of labeled examples are too few. Okay, so, just using only those you will not get a good accuracy. So, what do you do in such cases? So, these are the 4 types which we work on. So, let us first look at supervised learning. So, in supervised learning we have what is called a training data. So, the training data will consist of say n patterns. So, you have pattern x1, and you have y1 where y is your class label and x1 is your input data, which may consist of say a d-dimensional vector which contains all the feature values, the feature 1, feature 2, feature 3, etc. And y gives you the class label. Similarly, we have n such patterns, and y is the function where y is a function of x. So, depending on x you will have to find y. So, what we are doing in classification basically is to find a function h which approximates f. So, it may not be exactly f, but we find something as close to f as possible, that is the function h. And then when we come to classification, the output we have here, this y1, y2, etc. This could be either a finite set of values. For example, you can say you have 3 classes, class 1, class 2, class 3. So, you have a finite set of discrete values over here. So, that type of classification, that is what is called classification. But if the y is a real number, okay, so it is a real number, maybe it is some temperature or something like that, right, or BP or whatever. So, such a type of a value if you are getting, then the learning problem is called a regression problem. Okay, so what is supervised learning? Here x and y needn't only be numbers. Okay, x could be qualitative, okay, some values, etc. So, what you do is the h, the function h which we talked about is known as the hypothesis. So, what you do is you want to find the hypothesis h basically. So, that even on new examples which are not there in your training data also, you can get the class label basically. So, to measure the accuracy of the hypothesis, we have a test set. So, you have a test set of examples and you know the class labels for those. So, after predicting the class label, you see how many of them you are going to get right, and that will be what is called the classification accuracy of your hypothesis. So, what we want is we want a hypothesis which gives a high accuracy basically, and if it works well on new examples, this particular hypothesis we say it generalizes well. Okay. So, we want a hypothesis which generalizes well, because it means it is able to do well even on new examples which are not there in your training data. Sometimes what you do is you can use probabilities. Okay. So, you do not use just a function of x. So, what you do is you are finding out the probability, conditional probability distribution p y. So, probability that it belongs to a particular class given the example x. So, that is one type of classification that we are going to use. The output, if it is a finite set of values, for example, sunny, cloudy or rainy, or class 1, class 2, class 3, or in the case of digits class 0, class 1, class 2 up to class 9, etc. It is called classification. And if there are just 2 outputs, okay, so your output could be either 0 and 1, true or false, or something with just 2 values, just 2 classes, then you call it as a binary classification problem. And when y is a number, okay, then you call it as a regression problem, which we already spoke of, right. Okay. So, supervised learning, so we are trying to find h. Okay. So, we are trying to find the optimal hypothesis h. So, if you have different hypotheses h, capital H. So, what you are trying to do is you are trying to find the hypothesis which gives the maximum probability of H given the data. And using Bayes rule, this will be equivalent to this, right. Using the product rule, we can say that H star is equal to max of H data given H into P of H basically. So, that is what we are trying to do in supervised learning. So, what we will do first is we will look at classification, and we will look at a number of classification algorithms, and after looking at classification we will continue from there. So, the classification basically means assigning categories or classes to a collection of items. Okay. So, it is used to predict the membership of an item to a class. So, we can see it is something like this. So, here you have two classes, the triangle is one class and the circle is another class. And if you get a new pattern say P, then how do you assign it either to the triangle or to the circle. So, here also we have three classes. You can see that they have been separated by lines over here, or if it is more than 2 dimensions, you can say it is separated by a hyperplane. So, you have these three classes, and if we get some new pattern say here, which class do we give it to? Here similarly you have two classes with a separating hyperplane, and here this is the digits, handwritten digits 0 to 9. So, each of these will be a pattern which is given to you. So, there are a number of learning techniques or classification algorithms, supervised learning algorithms. So, some of them have been named over here: the decision tree, rule based systems, nearest neighbor classifier, Bayes classifier, support vector machines, neural networks, and a lot of others. So, these are some of the popular learning techniques which are there, and we will go through some of them to a certain extent, so that we can understand what is being done over there. So, before actually going to classification, let us see how we evaluate the classifiers. Okay, so, we have a classifier, and for example, for a problem, if we have found the decision tree which can be used to classify the patterns in that, how do we evaluate that classifier? So, the first way to evaluate is what is called the accuracy of the classifier. So, you will have a test set whose class labels are known. So, out of the test set, you see how many of the patterns are being classified correctly, and you get the accuracy of the classifier, classification accuracy, and this is a very important parameter. Okay. And we can also say, like if you get the classification accuracy as say a decimal number, 1 minus that gives you the error. Okay. Or in other words, if you have a percentage classification accuracy, if you do 100 minus that, you get the percentage error of that classifier. The second evaluation metric is what is called the design time and classification time. So, what is the design time? So, the design time is the time taken to build the classifier from the training data. So, in other words, suppose I decide that I am going to use a decision tree and I have this data. So, how do I induce that decision tree using the data that you have? So, that will take some time. So, that is what is known as the design time, and the classification time is the time taken to classify new patterns. Okay. So, let us see how this affects different algorithms. For example, the nearest neighbor classifier, it does not require any design time, because you are just using all the training patterns. Okay, you just have to keep all the training patterns and no design time is required. Whereas classification time is very high, because each test pattern has to be compared with every training pattern to see to which pattern it is the closest. Okay. So, once you find that, the class label of that will be the class label of this pattern. So, we can say that classification time is very high. On the other hand, if we take something like a neural network, the design time is very high, because you need time to design the network, okay, the neural network to I mean during the training. So, that takes time, but classification time is low, because you just have to take each pattern and go through the neural network and it gives you your output. So, it is like something you can look at it like a black box. You are giving in the input pattern and it gives you the class label immediately. So, the classification time is low in the case of neural networks. The third metric is the space requirement. So, suppose you are abstracting the finding an abstraction of the training set and then using that, then the space requirement will be much less. For example, if we take the say the neural network, you are taking the training data that you have, and the abstraction just consists of a network, a neural network, okay, with all the weights which are there in it. So, the abstraction is so high that space requirement is extremely low. But if we take the nearest neighbor classifier, you are going to store the entire training data. So, because you are storing the entire training data, the space requirement is much more. Okay. And even things like decision tree, rule based system, all these require less space, because there is an abstraction that is going on. Okay, the fourth one is the explanation ability. So, the idea is that you have a classifier, the classifier gives you some classification. So, how do you believe that classification is true? So, for that, if you can have an explanation ability which says that this pattern belongs to this class, because this feature has this value, this feature has this value, this feature has this value, etc., then you can believe it more. So, this is especially true in the case of the in the medical diagnosis, etc. Suppose your output is whether the person has cancer or not, etc., whether the person has some heart problem or not, then it is good if you can have some type of explanation ability. So, this explanation ability is available in some classifiers. For example, if you take a decision tree classifier, if you follow the path from the root node to the leaf node, it gives you all the rules that have been used, right, and that will give you an explanation. Similarly, if you have a rule based system, the rules which have got fired, because so the rules that have got fired, those actually will tell you why this has been chosen. But if you take something like a neural network classifier, in the neural network classifier, it is like a black box, right. It has been trained, the weights have been trained, and you do not know why it is happening. So, it is not possible to give an explanation giving the neural network. And the fifth one is noise tolerance. So, suppose there are outliers, okay, which means patterns which are not typical to the class, but they are appearing at the border of the class. So, how does it take care of that? And also, if you have patterns which have been classified wrongly. Okay. So, these things, have they been taken care of or not? So, that is what you have to see. Okay. So, what are the validation methods that you can use? So, what do you mean by validation methods? So, we have a training data and we have a classifier. Now, to check whether the classifier is good or not, we need to actually use it and see how it works. So, generally what you can do is that you can estimate this using the training data itself. Okay. So, this is what is called the resubstitution estimate. So, what is generally done is that you take part of the training data and use part of the training data to develop the classifier and use part of the training data to run the classifier on and get some type of an accuracy, which will tell you how good the classifier is. So, usually you subdivide it into smaller subsets. There are a number of ways of doing this. Okay. So, you can use one of the subsets for training and the other subset or the other subsets for validation. So, let us look at different methods. One is called the holdout method. So, in this holdout method, you are dividing the training data into two parts. Usually, it is taken as 2/3 for training and 1/3 for validation. But you can also have 1/2 and 1/2, half for training, half for validation, or sometimes you can have other proportions also. The second one is what is called the random subsampling. So, whatever you have done in the holdout method, you do it a number of times, okay, taking different patterns for training and different patterns for validation. So, if you do it say k times, then you find the average of these accuracies, and that is what is used. The third one is called the cross validation. So, what you are doing in the cross validation is that each pattern is used the same number of times for training and exactly once for testing. So, in the twofold cross validation, you divide it into two subsets. You use one for training and the other one for testing. Then you do vice versa, that is, you use the second one for training and the first part for testing, and then take the average of the two. So, in k-fold cross validation, what do? You divide the data into k equal subsets, and in each run one subset is used for testing and the other subsets are used for training. So, you are going to carry this out k times. A special case is when k is equal to n, which means each pattern is one group, right. So, this is called leave one out approach, because in every iteration that you are going to do, one pattern will be taken as the test pattern and all the other patterns are taken as the training pattern. So, this has to be repeated n times in this case, because your k is equal to n. Next is what is called the bootstrap procedure, where you just take out patterns at random from the data set and form a subset, which you use for training, and then you form another testing set again taken at random from your data set. So, these are different methods of validation that can be used for classification. Okay. So, this tells you what are the formula that is used. So, when we come to classification accuracy, it is equal to the number of correctly classified samples divided by the total number of samples. So, percentage accuracy will be into 100 basically, right. So, NC by N will be a value between 0 and 1. And here we have this here where we say the actual pattern and the predicted pattern. So, in the case of two class problem, say plus and minus, so you can have a pattern which whose actual class label is plus and the predicted class label is plus, or whose actual class label is plus, but predicted as minus, or it can be minus and predicted as plus, or it can be minus and predicted as minus. So, depending on that you will get what is called the true positive, the false negative, the false positive and the true negative. So, obviously, the total number of patterns you have is T p plus F p plus F n plus T n. So, you could also write this classification accuracy as T p plus T n. So, T p plus T n gives you the actually the corrected classified patterns divided by T p plus F p plus F n plus T n. So, C A can be written in that way. And then you also have what is called the precision and recall. So, the precision is equal to true positive divided by the true positive plus false positive, and the recall is equal to true positive divided by true positive plus false negative. So, these are all different evaluation metrics which can be used, especially when you have imbalanced data sets. You use the precision and recall. So, you make use of things like true positive, true negative, false positive, false negative, etc. in such a case. And yeah, so like I said, the classification accuracy can be also calculated using these values as true positive plus true negative divided by the sum of all these 4 values basically. Okay. So, now we come to all the classifiers that we are going to use. So, the first classifier that we are talking about uses the non-parametric models. So, what do you mean by non-parametric? It means that we are going to have a set of patterns and you are not using the distribution which is there in those patterns. So, each pattern is considered to be independent of the other, and it cannot be characterized by a set of parameters. So, for example, sometimes if you have a set of patterns, you can characterize them by taking the mean and the standard deviation of that set of patterns, etc., or find some distribution which is there in those patterns. Like it could be a normal distribution with the mean and standard deviation known. So, you know that all these patterns will be following this distribution, but in the case of non-parametric models that is not the case basically. So, what is the type of classifiers that we can use here? And after talking about the non-parametric methods, we will talk about methods like SVM, okay, which is also a non-parametric method, and then we will go into the rule based systems, and then we will talk about the decision classifier, okay, how you use the decision tables for classification. So, so that is the rest of the classifiers that we will talk about from now. So, we will stop here, and the next session I will start with the non-parametric models.